Okay.
All right. Can you see my screen?
Yep, looks good.
Perfect. So, hi, my name is Luis Lopez. I'm a software engineer at NSIDC. I know some of you personally, but if not, so I've been working on around the Pangeo ecosystem for a little while now. I'm currently based in Iowa. I'm originally from Chiapas, Mexico, the southernmost state. And another thing is that I'm into amateur astronomy and Raspberry Pis. So this is a very boring topic. It's not as flashy as the cool Pangeo visualizations that I've seen here, but it's really relevant for all of us that work with scientific data. So I'm excited about this work. Just some clarifications. This is not one of those presentations that at the end I'm going to tell HDF is better or Zarr is better. I know that that's what you were expecting, but no, this is going to be just kind of like presenting the work that some of us have been working around, working on this problem. It's not just me. Actually, this kind of started because we had a hack week last summer at the University of Washington. They organized a hack week around a mission called ISAT2. And at that mission, one of the things that I was kind of inclined to work on is like the access patterns for scientific data in HDF. So we have a long list of collaborators in the project. Some of the collaborators are here in the meeting. And I'll drop some links at the end if you're curious about more of this stuff. So I'll talk about the problem, some of the solutions that if you're not aware, you're probably going to I'm going to describe them briefly. And I don't think we'll have a time for a demo, but all of the code, it's executable. There is a gist on GitHub that you can test and you can see for yourself. So why this is important? Like so many of you, I work with remote sensing data, and non-trivial amount of that data is in this format that it's called HDF, hierarchical data format, which is an amazing format. It has its trade-offs, but the problem is that most of that data now it's being migrated to the cloud, and this is not a simple thing to work when you're in the cloud. And I'll go into why that is. There is a great post by Matt Rockling in 2018. Yeah, there is I think the title of the post or blog is HDF in the cloud, and he goes to describe like all of the issues with HDF in the cloud. And I feel like in some aspects we're in the complicated side of this XKCD. Like this is not a trivial problem or somebody have solved it by now. And the data is not getting smaller. So more and more data is being migrated to the cloud from different agencies in the same HDF format. So some of the solutions, right? Like this is not, this problem has been encountered and solved in different valid ways. For new missions, the simplest thing would be like, okay, try generating a cloud native format. Like if you have a new mission coming up, I myself are involved in a mission that from the start produces Zarr. It's called It's Life. So that's a great option. Like, and there are some great formats that are like friendly with the cloud, like Cox and GeoParquet, Flat GeoBuffer. That's fine, and it's a valid thing. But if we already have a lot of data from the missions or from model output that we want to analyze, well, then we have to try something different because the data is already in HDF. And there are some tools that we can use, right? Like H5 Coro is a library that a coworker of mine, JP Swinsky, started to work on at Goddard. There is Kerchunk, of course, that there is a lot of talk about Kerchunk on Pangeo. And if you're not familiar with Kerchunk, what Kerchunk does is extracts the metadata from the files, from the HDF files, and consolidates it into a JSON or Parquet file, so you can read it independently and faster. And you can also have custom services, right? Like there are many of those, or not many, but there are some. And this is the route that I was like more obsessed with, because I'm also the maintainer of a library that deals with HDF data mostly. And one of the frustrating things for researchers is once that they get to the data, it slows down their workflows. So I'm gonna explain a little bit why that is. Why HDF is not performant in the cloud? Well, there are a few reasons for that. First and foremost, it wasn't designed for the cloud. The HDF format as such has been around for decades. And its origins date from when we had different kind of computers and different computing models, workflows still. So that's despite that, I think it's a model, it's a data format that offers a lot of powerful features. But in the cloud, we have some problems. Like I think the first problem will be that we are still carrying the mentality that HDF should be like our hard drive. And I mean, we, the data producers. So we think about HDF as because the format is very permissive with what you do and how you do it. We do like this very nested trees with different information. We try to replicate it in a way models to not repeat information, and we ended up doing what it's called normalization of the data. So you have coordinates in one group, and then you have data about a variable in a different group. You try not to replicate the data, but then at the end, when you have that file flattened, you have to read a lot of the contents of the file in order to create a data frame that will be useful for your analysis. So that would be the main thing. And the other thing is that if you're working with the native libraries, they also were written for when we had like really fast access to disk, and this is over the network. So one of the main issues with the library is that it has a global lock, like similar to Python, that doesn't allow the library to do concurrent requests. And when we're reading this metadata by default, right? Like if we don't do anything by default, it's 4 kilobytes in chunks of 4 kilobytes. I'm talking about the metadata itself. Then we have a problem. And this is not just a problem of the format. This is kind of a three-body problem where we have the format, we have tools that access the format, and we have the size of the problem. So there are three different things that we want to address or should address if we're doing this at scale. The size, we cannot go around that. Like that's why we are doing cloud computing. That's why we work in HPC. And there is no like, oh, the data is going to get smaller, as I said at the beginning. So there are no other workarounds that accept using platforms that allow us to do this with bigger data. Now, the things that we can improve are the tools and the format itself. This diagram on the right represents a little bit of how things are accessed in the cloud. Like you have, your different tools at the top. You can be using QGIS, GDAL, a Jupyter Notebook, a portal that does, talk to some domain-specific API, and then you have, and this is HDF, right? So file drivers, GDAL has its own C bindings for the HDF library. And then depending on where you're talking to, the HDF library can be using one of these drivers on the left for local access, or we can do use libraries on the right for remote access. Like the HDF library has one that is called ROS3 or read-only S3 access. Then we can have file-like objects like FSSpec. And there is another one that somebody presented at SciPy a little while ago that I think got a little abandoned, but it works. And that's how we get to these buckets of data, these terabytes or petabytes of data, right? And before we dive into like what is cloud optimized HDF, a little bit about why Zarr does amazingly in the cloud. Well, you are all familiar, I'm sure, with Zarr. One of the reasons why Zarr is it's awesome is because exposes the internal metadata, flushes out the file into like the different parts, the different components. The metadata can be consolidated, so it's only one file that you get the file, and then you have all the stuff that you need to decode the chunks. It tells you the filters, it tells you the compressions used, and where the bytes are in the object. And another great thing for the cloud storage is that the chunks map directly to the cloud object. So all the optimizations that you can do caching at the chunk level, or S3 does at the chunk level, are apply here, because then you have your chunks in these cubes, and those are the objects that S3, for example. It will be the same with Azure and Google Cloud. And another great thing is that the I/O can be parallelized. So there you're not limited by the HDF stack, right? And finally, you can have new features coming up to the stack very easily because it's a new format. So you can implement stuff like GeoZarr, appendable storage, and all that good stuff, which you cannot do it at the same speed in the HDF library because you'll be probably breaking the code that works at Oak Ridge National Laboratory that doing supercomputing simulations, right? So it's the trade-off of being a new format versus a very well-established format. So this is kind of a joke that this is a poster from Alexander Genelak, the architect from the HDF group, that presented at the last AGU. If you see this poster, I wouldn't stop because, like, what is this? It's not flashy. It just like shows you some code and some, I don't know. And but then when I was talking to him and so you guys presented this, they started to work on some of the features that Cloud Optimized HDF is about. He said, oh yeah, we had a poster at AGU, and then I was like immediately drawn to like, okay, so what we need to do in order to do these cloud optimizations for the HDF file format. And it occurred to me that it was kind of like the LK99 moment, like the people that were at that meeting with him would try to replicate it with mixed results. We try to levitate the HDF by doing this optimization. So what you're seeing here in the poster, it's nothing different from what the advantages that COG file has, for example. You have the metadata consolidation, you can have different chunk sizes, and you cannot get rid of the global lock. That's still there. And there is a link there that will take you to this poster, and you can take a look in detail of what this is. So this is kind of a joke also that when I first did the repacking of the file and I opened it with Xarray, this is from a mission that is called ISA2 that has a lot of variables and nested groups and all of that. So it's very time consuming just to opening the file. When we did the repacking and the metadata consolidation, I got those numbers and I got really excited. I posted this meme, and Joe, a coworker that works at ASF, he replied with those words that I'll be waiting for the list of big if I tell you that it works, right? And yeah, there is a list of if, like the first one that you have to reprocess the file if it's already there. But it works. And I got really excited. This is when we arrived to the ISAT Hack Week meeting, kind of like the idea that we can replicate this at scale. And unfortunately, that wasn't the case. So we did it with more files, bigger files, and not only we got better numbers, we got worse numbers. Like we got like numbers that were not reflecting what we were expecting. The only library that took advantage of the consolidation and all of that was H5 Coro, which is this library that does concurrent reads for HDF file, a subset of the schema, not the whole thing. And you can see, like in Xarray, we make things worse, like 1.5 the time that we originally took. And I was puzzled by this. So we stopped working on this. This is just a week that we work on it. Then I pick it up in December for AGU. And this is kind of what was happening. Like when I started debugging, like, okay, so say I'm in Python, I'm using the Pangeo stack, the typical, X-array, open this file. This is a remote file, by the way, right? So I felt like this cat for like a little bit more than 2 weeks, trying to understand the different aspects of the stack when we access the files. So you have X-array that in turn, I'm missing some components here. Like internally uses an engine that is called H5 netcdf that does interface with the H5 library, which is just the Python bindings of the C library that you get. And the HDF library has 2 ways. Well, there are more, but the main 2 ways that you can get to data is using either the read-only S3 driver that is native to the library, or opening a remote file system with FSSpec and using the file-like objects, right? And then you get another layer of complexity, which is the NASA policies that if you're in the cloud, it's one thing. If you're not in the cloud, it's a little bit different. This is only for NASA. In NOAA, you probably won't have this layer of complexity, but all of these layers have a mind of their own. You basically have to tell each library what to do, and out of the box, well, this wasn't working clearly. Here's a little diagram of the different things, the different moving parts and parameters, and how you get to the files. With X-array, you have a driver set of parameters that you get. Those are passed to the engine. In this case, it's H5 netcdf. And if you have, that those drivers don't apply to what netcdf gets, then it will pass them to the actual engine, which is H5 and that's when the fun stuff started. So one of the things that I ran into or find out is that basically you have to have 2 access patterns for the files. If we're talking about cloud optimized HDF that was consolidated using one of the many strategies, and you're using a regular file, you have to not fine tune because it's not like 1,000 parameters, but basically you have to fine tune some of the parameters to align with the consolidation or the cloud optimization strategy that we took to consolidate that file. And if we do that, then we get performance out of it. And for this to work, you need to be using the latest versions of the library, the HDF library. And I did some modifications to FSSpec as well to track some of the I/O to make sure, right, like that we were actually doing what we thought we were doing. Another aspect of this is that the default cache behavior in each of these libraries is not optimized for this kind of access pattern. So H5 or the HDF library has a caching mechanism that doesn't align with what FSSpec does in terms of caching. So the 2 libraries kind of collide, and you get like that performance that you saw at the beginning. Once that you have that figured out, this is what we get, and I'm really excited about this. So we did some replotting with different tools. The color that I think it's important here in this chart is the blue, because that's what we get once that we optimize the files. We cloud optimize the HDF files, and we tell the library that we're dealing with a cloud optimized HDF. You can see, I mean, like the first thing that I can notice is that once that we have this cloud optimization and alignment of the access pattern with that cloud optimization, you can have X-array accessing the HDF at the same speed or even faster than Kerchunk, which is not, I think it's amazing. One of the benefits of this is that you don't have to create Kerchunks, right? Like if you create I think that we should to support a different access pattern, but if you start producing these cloud optimized HDF files and putting in the stack catalogs, then you wouldn't need to do that. Or you can have it as an extra access pattern. And of course, the most performant way of doing it is just with H5 because it's not decoding, the CF convention stuff, and that you get to the data without doing all of the fancy and cool stuff that X-array does. And H5 core benefits as well. The libraries that are like designed for this concurrent access, that's where H5 core takes the speed from. It's not limited by the lock. Also benefit from it. Another side effect of doing this that has to do with the reads to the file. If we cloud optimize the file, we won't have a lot of I/O, which for the data producers could mean a lot of savings because I'm thinking of AWS, they charge by GET request to a bucket. So if you have these big files and we're advocating for cloud native workflows, then you're not copying the entire archive. You're just opening for the information that you need. And the thing on the right is what will happen at the moment. You'll be issuing like 4,000 requests or more, depending on the data set. And on a cloud optimized HDF file, we only needed 16 requests, bigger requests to the data, metadata first, and then to the actual chunks of the data. So that's orders of magnitude and potential cost savings for the data producers. And now let's imagine a world where we're dealing with cloud optimized HDF file. What are the cool things that we could do with that? One of the things that we could do with that is that not only we will be taking advantage of the speed natively is faster, but you can also be making the downstream tools and services faster too. Not by a lot, but if you're dealing with a lot of data and you have cloud optimized HDF, you can make a huge impact in access speeds for and egress for all of these different tools. So you can have Xpublish or Kerchunk. This is a little bit of a weird semantic mix-up because I don't know what part of the Kerchunk will belong to Stack and vice versa. But I'm imagining a future where the Stack spec has a kind of an extension where it will tell you basically what Kerchunk tells you, like where the bytes are in the HDF. So then you only have to load the Stack catalog. You don't have to deal with Kerchunk directly. But you can have other tools, or you can open the files directly, and it'll be faster. Just if you're working on a Jupyter notebook, that is most of what we do on a day-to-day. So as I said, I'm really optimistic about this. This is preliminary. I submitted a tag to SciPy that I hope it gets accepted to expand on this. The problem, format, size, and tool. Size, we cannot do anything about it. Cloud computing, we should make it more accessible. Format, cloud optimized HDF, it's a thing and it works. As of now, we need to know a few things on like how to align the access pattern to the strategy used for those files, but it works. The caching and chunk size can be as fine-tuned. The data layouts, that's important. Data producers should start thinking about like not replicating this mentality of HDF is just like a tree in my directory, and I'm gonna put everything like 4 levels down. And the tools need to be modernized too. So all of this should live in the HDF core specification and stack. The libraries that read HDF natively should be aware. Like now, we don't think about COGS and TIFF because all the libraries deal that automatically. When you open a COG, the library knows what to do to make it efficient. But that requires a big investment on the HDF itself, and it's like I was looking at the other day, more than 1 million lines of code of C. So you have to do something there. Some libraries contain advantages of this, and we also need a lot of training to like be aware of why these access patterns matter, what we can do to make things faster, and I think that's basically it. As I said, this is a very preliminary but promising work. thank you for listening, and I'm happy to answer your questions if you have any.
All right, thanks, Luis. I'm going to stop the recording.